Now the question arises, what is an atom? In biology you have studied that a living body is made up of building blocks, the cells. If you look at a building, what does mason do? He keeps making layers of bricks and finally a room is made, then many rooms together, a building. Or if we take the case of high-rising buildings, first they make one floor in which there are many flats, then the second and then the third, and ultimately there are say about hundreds of flats or apartments in one high-rising building alone. Similarly, in the case of matter, there are atoms as the building blocks. When you were small, you remember what you used to do? You used to play with blocks. And with the help of blocks, you would make a pyramid, sometimes a palace, sometimes a robo. So actually what were you doing? You were joining up small cubicles. So here also there are atoms. But these atoms are very, very, very small. So small that they cannot be taken they cannot be seen with naked eyes. If we try to understand the relative size of atom in terms of their radius, what we find is that in case of water, the radius is 10 raised to the power of minus 9. In hydrogen, 10 raised to the power of minus 10. Sand grain is 10 raised to the power of minus 4 and an ant 10 raised to the power of minus 2. How can we measure an atom? You know, for measuring there is always a unit. In the case of atom, because it's very small, the unit we use is nanometer. Which is denoted as nm. So what we find is 1 by 10 raised to the power of 9, m is equal to 1 nanometer. So you can imagine how small is a nanometer? Or you can say 1 m is equal to 10 raised to the power of 9 nanometers. So if so many nanometers are together, then we get 1. So that's about the size of the atom. If more than millions of atoms are stacked together, they form a layer which is as thick as a paper. So these are the examples by which you will come to know how small an atom is. Now, how are we known? By our names. Sometimes our families or parents or even friends, they keep some pet names also, some short names. That's exactly what chemists do. In olden times, what they did, they wanted to denote an element with the help of say, a picture or a design. Like they used a dot in a circle for hydrogen, an empty circle for oxygen, and a shaded circle for carbon. But later on, they developed and devised a method by which they had proper symbols for all the elements, so that it becomes universal. That means all over the world, same symbols are used. So it is easy to understand. And also, they are short. Now, for this also there had to be some method. The simplest method was that they used the first letter. So many symbols got devised. For example, hydrogen, obviously H, oxygen, O, nitrogen, N, phosphorus, P, sulfur, S. After some time they realized that there are some elements which start with the same letter. Now what to do about that? Now for example, say let us take the case of calcium and carbon. Both start with C. To carbon they gave C, now they can't give C to calcium also. So they said, okay, never mind, you can use first two letters. So in the case of calcium, it becomes Ca. But if you notice carefully, first letter is in capital and second letter is in small case. So like this, the second thing they used was two letters. Now, still there was some problem because there are more cases in which they start with the same letter and even the first two letters may be same. So what they did, okay, never mind. Now in case of say calcium and cobalt, they used first two letters. But in some other cases, they wanted to use two letters which may not be first and second, it could be first and some other. For example, in case of chromium, it is Cr. In case of chlorine, it is Cl. Now, in this case, both the first two letters were same. First the problem came when the first letter was same. So they used, okay, we'll use the second letter. But now what to do? Even the second letter is same. So they said, okay, nothing to worry. We can take first letter and any other letter. And the same principle, first letter in capital, second letter in small case. In addition to this, some symbols were also derived from Latin names. For example, iron in Latin is known as ferrum. So, it was given a symbol of Fe. Sodium in Latin is natrium. Symbol is Na. Potassium is kalium. Symbol is K. Similarly, cuprous, Cu. So like this, a certain pattern was set by which all the elements were given this. Now, can we create our own symbols? We can't, because they will not be universally acceptable. For that, there is a body called International. The letter we use for this is I, union, U of pure and applied chemistry. So, IUPAC is an international body which approves the symbols. Now, what does a symbol denote? A symbol denotes the name of the element, and its quantity. That means how many atoms are there. After this, we come to atomic mass. What is atomic mass? Atomic mass is the mass of an atom. Simple. Now, how do we measure it? In physics, in measurements and weights, you must have studied that we take a standard weight. In olden times, when there were no standard weights and measurements, how did they measure? By the span of their arm. So, by measuring with span of arm, they would say, okay, this thing is 10 spans. Now, but the size of the arm can vary with people. So, this is not a standardized measurement. So, in the case of atomic mass also, because atom is very small, how to see? How we can't weigh it? So, it has to be in relation to something. All weights and measurements are relative. They are in relation to something. So, here also this was in relation to something. So, first atom or first element that they considered for creating a mass was oxygen. Now, the question arises, why did they choose oxygen? Because oxygen is combined with most of the substances, metals, non-metals, it combines with all. It combines with all elements. Second convenience was that when we relatively weigh or relatively assess the mass, we found it was always in a whole number. The ratio was in whole number, nearly whole number, if not exactly whole number. So oxygen was almost always in whole number. However, later this was changed. In 1961, the basis they decided was carbon. Now carbon atomic mass is 12, so the basic unit of atomic mass is 1/12 of carbon atom. So we have taken C12 as the basic or the basis of deciding on atomic mass. So we can say if oxygen atomic mass is 16, then that means oxygen is 4/3 of carbon. Or if you are going to weigh, if on one side you keep say 4 atoms of oxygen, then on this side if you want to weigh it with carbon, there will be 3 of carbon. So then they become equal. So like this they were able to work out the atomic mass of all the elements. The atomic mass of oxygen is 16 and that of carbon is